Sıradaki konuşmacımız StackHPC kurucu ortağı ve CTO'su Stig Telfer olacak. StackHPC kurucu ortağı ve CTO'su Stig, başta HPC ve yazılım tanımlı ağ oluşturma alanlarında çalışan, çeşitli önde gelen teknoloji şirketlerinde Ar-Ge geçmişine sahiptir. Bulut, HPC ve yapay zekanın yakınsaması üzerinde çalışmaya devam etmektedir. Stig aynı zamanda akademik bilimsel araştırma kullanım senaryoları için OpenStack'i kullanan, küresel olarak dağıtılmış bir araştırma kurumları grubu olan OpenStack Bilimsel Özel İlgi Grubu'nun eş başkanıdır. Şimdi konuşmalarını yapmak üzere Stig Telfer'ı sahneye davet ediyorum.
Good morning. It's really good to be here. Hold on a second. I'm going to be speaking in English. I don't speak Turkish. I'm very sorry about that. But I would love to, but we have really awesome translators. And thank you so much for your work. Translate that. Hey. We good? So, I come from England, and okay. You probably haven't heard of our business. We started a company 8 years ago, StackHPC, and the company that we created is focused specifically on the requirements of research computing. We started with these 5 goals, and really, in the last 8 years, we have stuck to those objectives very closely. We work to develop OpenStack for research computing use cases, and also we work to develop scientific computing to work better in OpenStack cloud environments as well. We also work to provide infrastructure, develop new capabilities in OpenStack to support high-performance computing technologies, and we do what we can to help train people and to argue for the case for OpenStack and for scientific computing to work better together. Our company is a strong believer in open source and has been from the beginning. We were the 3rd most significant contributor to the latest release that Thierry was talking about, the Caracol release. So I wanted to talk a little bit today about how OpenStack works well with other open source technologies to implement scientific computing. And to give you an example of the kind of use cases that we work with, we may have customers who have users who want to run a batch compute, high-performance computing environment such as Slurm, with parallel workloads running MPI. Next to them, there may be people who want to just come over and run some data science, run some analytics or some visualization of their results. And maybe there are other people who want to run bigger laptops. So they want to move from working on their own laptop to working in a cloud environment or working in a space with more capacity, perhaps with a Linux or a Windows desktop, perhaps with GPUs. There may be other people within the community who want to run a training workshop on machine learning and AI, because that is a hot topic, and maybe they need infrastructure with GPUs to be able to do this. Alongside them, there may be people who want to run a production service using Kubernetes and using that and publish a managed service from their OpenStack environment to provide a web interface for their scientific community. And then finally, there may be people who want to run trusted research. So they want to do research on medical data, genomics data, or data that is very sensitive for trade secrets or other things as well. We try and combine all of these people and meet all of their needs using one single research cloud environment. The interesting thing is that high-performance computing itself is getting tremendous pressure for change. Software-defined infrastructure, the kind of thing that we make with our OpenStack clouds, is changing the nature of high-performance computing itself. In 2020, the lead of the Swiss National Supercomputing Center, said that their new supercomputers would be running with software-defined infrastructure. It's not OpenStack, but it is software-defined. Alongside that, there is the human requirement, or the human change, which is around this idea of building the skills for DevOps. And this is probably the more important transformation than software-defined infrastructure itself. Building those human skills is a tremendous challenge, but has tremendous benefits. Once we do this, we can start to bring in these sort of non-traditional high-performance computing workloads. Workloads from social sciences or from life sciences and genomics, not conventionally thought of as high-performance computing. Because of machine learning, they are bringing in demands, and data analytics. These are all creating new requirements for high-performance computing. And of course, there is machine learning and AI, which is cutting across everything. OpenStack, thankfully, is going to save the day. Talking about AI and research computing, I wanted to mention a particular client that we have been working with, the European Centre for Medium-Range Weather Forecasting. They have been working at the forefront of this idea of using AI and generative AI for helping to assist with the forecasts that they generate for a fraction of the compute resource that the numerical weather models conventionally use. To build these kinds of environments, we use OpenStack, and we use the Keynote project and Collar Ansible within OpenStack to build up an infrastructure as code. We combine Nova and Ironic to mix virtualized and bare metal compute resources, and we use neutron and OVN networking with accelerated offloads, which I will talk about. We must also show the resources and their utilization to the clients. So we use CloudKitty for this, Keystone for federated identity management and authentication, Designate because it's awesome, and Manila for sharing files and file systems within our environments as well. A lot of research computing environments think in terms of parallel POSIX file systems. These are very important. The last two, Magnum, containers as a service, and Blazar, which is probably the only service that maybe you haven't heard of, enables us to manage future reservations and guarantee fair sharing of scarce resources in our clouds, like our GPUs. We also use open source technologies, Ceph, OVN, Ansible, and Kubernetes, Linux, of course, and the last one, Azimuth, is our own open source cloud portal. The way that it works, imagine that we have a bare metal compute cloud, which looks like this. Day one, we might provision a giant Slurm cluster to get the high-performance computing numbers so that we can publish how big our supercomputer is among the others around the world. Then we scale that back to a right size for steady-state usage, and we start to provision other things in this nice dynamic way on our reconfigurable infrastructure. Maybe we build Kubernetes and Jupyter Hub, and then we can do something quite interesting, which is to provision hypervisors as a workload on our bare metal cloud. We can also build in bare metal resources for trusted research. And then we introduce a project who maybe only has access to virtualized resource. So they put in a machine learning environment using Kubeflow and virtual desktops using Guacamole. Maybe also then we start to overspill and use our Slurm compute cluster and start to use some unused capacity in a dynamic way. Build up some more Kubernetes. We see that the hypervisors aren't being used, so we put in more Slurm. We can manage the resources in this kind of very fluid way, which previously we could not do. And this is the power of the software-defined supercomputer. We can combine bare metal, virtualization, and containerization together, bring them all into one infrastructure, and let the users build what they want. I'm going to talk a little bit about how we do that, and this is a little bit more technical. So, when we're looking at making a virtualized high-performance computing compute node, we try and use a lot of tricks which enable us to optimize the performance and make that virtualization layer much thinner. Each of these has advantages in performance, but costs and compromises in terms of flexibility. We pass through the CPU's host model so that we can use things like vectorization. We get the maximum performance from our processor. But at the same time, if we have different machines of different generations, it means that we cannot move virtual machines between the two because we can see the difference in the instruction set. We pin the CPUs on our virtual machines to the physical CPUs, and we pass through the topology of the NUMA regions of our processors. This means then it makes it a lot harder for Nova to schedule new virtual machines into the spaces left available and the free gaps, the Tetris problem. We put static huge pages, gigabyte pages of RAM in our hypervisor, and we reserve those for the exclusive use of our virtual machines to optimize memory translation. This makes it quite difficult because quite often the Linux host will not see that we have 95% of the RAM reserved for our virtual machines. It makes assumptions about how much RAM is available. Sometimes this hits problems. Finally, we use hardware-accelerated networking technologies such as SRIOV with software-defined networking offloads. This adds a lot of complexity in the way that we build our OpenStack hypervisors. It's quite hard to maintain for the admins. Last point, we add BIOS configurations for AMD EPYC processors to maximize the number of NUMA regions to give optimal performance. And this can create more partitions for our CPU cores, leading to greater fragmentation of those physical resources. We take the rough with the smooth. We strike a compromise at the point between flexibility and performance, which suits us well. OpenStack enables us to do this. We choose our own adventure. Imagine we're building our hypervisor, and we have a two-socket AMD EPYC system, for example. We might save some CPU cores for our hypervisor to do the housekeeping work that a hypervisor does. How do we share the rest of the cores between our virtual machines? And I show you a little example of how the trade-offs in high-performance computing play out in a virtualized environment. Maybe we want to say we put our virtual machines onto two of our NUMA regions. So this is a NUMA region, these are CPU cores, this is the CPU socket. So we build a virtual machine, we fill up two NUMA regions with our CPU cores. Then we build another virtual machine, we put it on another two, and so we fill our hypervisor in this way. And each of the virtual machines has access to two NUMA nodes and the memory performance of two NUMA nodes. Maybe we want to give it more memory bandwidth, and so we build our virtual machines so that they see all of the NUMA regions of one socket. So now it has half of the dual socket capability. We fill up our machine like this, and now our virtual machine has all of the memory bandwidth of one socket and all of the locality of one socket. But maybe we want to maximize memory performance, and we put our virtual machine across both sockets and 8 NUMA regions, and we build up our hypervisor like this. What is the difference? So we get full memory performance from the system. What is the effect of that? Let's find out. If we put in the 2 NUMA sockets, like this up here, and we add 4 virtual machines, and we use memory benchmarks to test the performance of each of those virtual machines. 1, 2, 3, 4 machines all at the same time. We see the same performance all the time. This is nice, because actually it means that my virtual machine here does not see the effect of its neighbors. But it's also kind of slow. We use the whole socket, we get almost double the performance. And actually then we get the same fair degradation, so actually we go down to a lower performance when the other machines on our socket are busy. Using 8 NUMA nodes, we get even better performance, so we get 200 gigabytes a second of memory bandwidth in one virtual machine. But when we see the other activity on the system, we are a noisy neighbor, and we see that our machine's performance degrades when other people are using it. The trade-off we make, it depends on the use cases we have. Oh yeah. So this is easy to make in OpenStack. We can just configure our virtual machine flavors using properties and attributes like so. But there is a problem, and this comes back to what Thierry was saying about gaps. In an OpenStack system, we can't actually put all of our NUMA nodes on the same socket. OpenStack is blind to the physical proximity of the different NUMA regions. We can only do it by hand. So this is something that within StackHPC we are working to improve and fill this gap. Upstream we will be proposing changes to enable us to visualize the physical cost of different NUMA placements and find the best affinity. Together as a community we will fix that. The effect of going wide, having 8 NUMA regions, we can see when we look at the bandwidth, or the latency between threading operations. We use a protocol called OpenMP, and we can measure the effect of our different NUMA models, 2 NUMA nodes, 4, 8, and this performance of the underlying hypervisor. And we can see the latency here, so lower is better. The latency of our different benchmarks here for different inter-thread operations. And we can see that a lot of them have a clear difference between 2 sockets and 1 socket machines. So we can see the effect of going from 1 socket across the motherboard to the other in this graph. We can also see the difference in performance between bare metal running on a bare metal compute node and running on a virtual machine across 8 NUMA nodes. And it's not that big. Next, how do we make the fabric for the network? How do we join together our compute nodes as a parallel workload? This is very important for some of those people running Slurm jobs, OpenMPI, parallel compute jobs. There are 2 ways that we do this. And the first way is to use SR-IOV, hardware passing through into the virtual machines and using them directly as a message passing communication interface. For this, we see about 1.6 microseconds, which is what we normally see for a bare metal Ethernet environment. On a 50 gig Ethernet NIC, we get 49 gigabits a second and 4 million packets per second transmit rate. Not bad. The next way to do this is to combine together SR-IOV with the ability to do bonding and software-defined networking offloads. This enables us to use 2 network cards together and present a single hardware interface from it. We get much higher latency, still good, but we get very good bandwidth as well. The way that this works is we have a physical network card with 2 ports. Behind it, though, in our virtual machines, we see 1 interface, which represents both ports. It's very powerful. When we test this, we see the effect of a hypervisor. And so our virtual machines on 1 hypervisor, we measure the latency between 16 virtual machines here, placed on 4 hypervisors. We see that the locality gives us about 1.6 microseconds between virtual machines, about 3.5 to 4 between virtual machines on different networks. The performance for different software-defined networking layers, and this is Kubernetes running on top of OpenStack, we get a bandwidth of about 180 gigabits a second in this case. That's really high. But the most important thing is that high-performance computing has this strange idea of time. We focus a lot, we spend a lot of time trying to work with really hard platforms. And yet we do that just to make our runtime of our applications slightly shorter. How do we make our compute platforms easier to use so that with time we're measuring is the time for our scientists to get the results? And for this we need a user-friendly environment that they can adopt. In StackHPC we have an open source project called Azimuth, which works on top of OpenStack a bit like Horizon, but focused on platforms for research computing. It enables us to have our users make their own machines, but it doesn't mean that they have to become system administrators or cloud experts, or they don't have to wait for people within the research computing operations team to be able to do this. They can make it themselves, and the platforms that they make represent the best capabilities of the system as well. Azimuth is supported by all of these people and has been developed in partnership with them. The way it works, it is a web portal for self-service. It provides a catalog of applications, which I will demonstrate shortly. The applications are or the platforms are implemented using standard tools, Terraform, Ansible, OpenStack, Helm, and the managers of the service develop or deploy these applications and configure them to make the best integrated use of their cloud environment. For a user, this is what it looks like. We log in, and we're asked to create a platform. So it says here, create a platform. We get the catalog. The catalog is very big. It's off the page. We choose something we want to use. Maybe we're looking for a bigger desktop, so we want a Linux workstation. We choose the Linux workstation. We say how big it is and how much storage it needs. We provide the simplest options, but no simpler, for the scientists to make good choices. Then it says how big is that machine and how much quota, how much spare resource do I have. Then the machine starts to build. In the background, this is running Terraform and Ansible to configure this system. The user does not see that. When it is ready, the user can access the system, see the properties, and services are exposed from our system. In this case, a virtual console and monitoring for our desktop environment. We go to the console using Guacamole, and the first thing that is interesting to see is that we access it through this very long obfuscated URL. There is no public IP for this machine. It is safe by default. Everything is behind the portal and accessed through this encrypted, authenticated interface. It is secure by default. We access our desktop, and then we can also see the monitoring for how our machine is performing as well. Maybe we want to deploy a Kubernetes environment, and Azimuth also does this using Cluster API. Cluster API interfaces between Kubernetes and infrastructure, and is a very popular project across the Kubernetes community and has strong OpenStack support that we have contributed to. So we choose Kubernetes, we choose a version of Kubernetes that we want to run, and then we say, well, how big do we want to make my machine, our cluster? And then we see the effect of that on our quota, and it goes off and builds. The machine is installing, a nice example here, a lot of operators and add-ons which are optimized for our cloud infrastructure. We add GPU support for free by default as standard in this cloud in case the users want to use GPUs. Similar for RDMA and monitoring and other things such and so on and so on. Our machines are building, and then it becomes ready. And then we can access the Kubernetes config if we want to talk to it directly, or we can use it for building other things. We see the dashboards and monitoring, including monitoring of our GPUs. A nice way that we can use it is for data science. Data science using Jupyter environments, interactive Python environments, and building on that with task flow computation using Dask. Dask is a project that builds on Jupyter to add distributed processing. Now we want to build it onto a Kubernetes cluster. It's deployed as a Helm chart instead as Terraform and Ansible. And so it has the flexibility. It is downloading the containers and operating the Helm, deploying the Helm chart. It becomes available. We access a Jupyter notebook in the usual way. It is logged in as me, well, not me, but my colleague Matt. And so authentication is passed through. There is no logging in again. And we can see the effect of running a single session behind this authenticated portal. There is our Jupyter notebook. There is our data distributed task processing. But we can also, remember there was somebody who wanted to provide a training workshop for a bunch of users. Maybe they want to provide some GPU or machine learning training. Those users might not exist in the OpenStack environment. They want to create a workshop just for 20 people from another university or something like this. We can also add, using Keycloak, we can add users who don't exist in OpenStack but do exist inside this Jupyter Hub environment. We can add them just to access the interface for Jupyter Hub, but not for the monitoring. They log in, and they get a notebook created just for them. It is all managed within the platform. Finally, because this is a high-performance computing environment, we can also create batch-queued environments such as Slurm, very widely used within scientific computing. In a Slurm case, we choose the properties of our cluster, how big we want to make the storage, how many compute nodes we want to have, and it will go off and it will provision the Slurm cluster in the same way. It is deployed using Terraform and Ansible, and then when it becomes available, we can get the information about how to log in and run batch jobs. We can see user-friendly web interfaces like Open On Demand, which is popular for using with Slurm. And also we can see monitoring of the jobs that have run within our system. Azimuth provides a nice integrated package which is customizable by research computing users. So we make the jump. We jump into an high-performance computing research cloud, but we're not doing it alone. There is a large group of people out there in the OpenStack community who are also doing the same transition, the same journey into using open cloud infrastructure for research computing use cases. This QR code is available for anyone who can join. There is a Slack channel where the members communicate. It's not too busy, but there's about 270 other institutions present in this environment as well. So I think on that note, I should say thank you. That is the same QR code. Thank you for your time.